Well, thanks very much, John. That's a very nice introduction, and I'm really pleased to be able to talk to you. I was an undergraduate in Aberystwyth many moons ago, which is actually where I started climbing, and sort of one thing led on to another. I'm still very good mates with the people I climbed with back as an undergrad in Aberystwyth, and we used to take off to North Wales for 4-day weekends and do lots of climbing, and that's where my interest in climbing and mountains really started. This talk is going to be on the tectonics of the Himalayas, and it's mostly a generalized talk about, I'm going to show you some pictures from Ladakh and some pictures from Zanskar, and mostly around the Nepal region, Tibet, southern Tibet and Nepal, particularly on the Mount Everest region, which everyone seems to be mostly interested in. So this picture here is taken from the space shuttle, looking roughly over Kathmandu, looking west along the arc of the Himalayas. The Himalayas are bounded by these two major faults, the main central thrust and the South Tibetan detachment, which is a low angle normal fault, which means all of this high temperature, high pressure rocks of the greater Himalayas were extruded to the south, bounded by a thrust at the bottom and a normal fault at the top. This is a process generally called channel flow at the moment, which I'll come on to a bit later. The other major tectonic argument is one of continental crustal escape, which was originated from Paul Taponnier, Peter Molnar, 40, 50 years ago now, where the thickened crust of Tibet was extruded eastwards out of the way of these major strike-slip faults. I'm not going to talk about this much today at all, but I am going to concentrate along the Himalayas. So why do we study the mountains in the Himalayas and Karakoram? Well, partly because they're very young. It's an ongoing mountain belt. Himalayas has been active for the last 50 million years. And the regions to the north in the Karakoram, this picture here is taken from the same height as the summit of Trango Towers. This is the Great Trango Tower here with 2 kilometers of vertical elevation different. Nameless Spire, which is one of the great climbing routes of the Karakoram. And this is the highest man-made structure, or it used to be. It's now overshadowed by the one in Dubai, which is a little bit higher. And the reason we study the Himalayas is fantastic 3-dimensional exposures through a very young, active mountain belt. So the Himalayas are part of the Indian plate. And India, as I'm sure you knew, is part of Gondwana land. So it was attached to the southern continents of South Africa, Madagascar, Antarctica, and it rifted away something like 120 million years ago. India became an island, and it moved very rapidly across the Indian Ocean to collide with Tibet along the Indus-Sucha zone, which is now beautifully exposed in Ladakh and right the way across southern Tibet, all the way down here through the Indo-Burman ranges. And you can trace the ophiolite sequences all the way down here through West Pakistan, down along the Chaman Fault system. So here's a simplified sketch map of the Himalayas showing the major structural boundaries. The Sucha zone is here, variously called the Indus-Sangpo or the Sangpo-Brahmaputra Sucha. The southern margin of Asia was largely Andean-type granites, subduction-related granites. The upper crust of the Indian plate is this yellow sequence here, which is the Cambrian Phanerozoic sedimentary rocks that form the passive continental margin of India. And then the high-grade metamorphic rocks are these ones in this sort of rather ghastly purple color, bounded by the main central thrust along the base and this low-angle normal fault along the top. And then the lesser Himalayas are a very low sedimentary sequence, mostly Proterozoic, going back to the Paleozoic sequence of Indian plate sediments that have been very hardly metamorphosed at all. So when you reconstruct all those rocks and unwind all the folds and thrusts of the Himalayas is a remarkably simple mountain belt. The structures are pretty consistent for about 2,000 kilometers along strike, at least from Ladakh, Kishtwar region in the west, all the way to Arunachal Pradesh in the east. And when you reconstruct it, the Indian plate, the Himalayas, bounded today by the active main boundary thrust, These are the two faults I pointed out recently on the previous slide, the main central thrust and the South Tibetan detachment. So all of these rocks are now high-grade metamorphic, and this is the shelf carbonate sequence that form the northern passive margin of India. And there's one horizon here, the Neo-Proterozoic, that you can trace all the way from the Lesser Himalayas through the Himanta group of the High Himalayas, the protolith of all the high-grade sillimanite gneisses of the Himalaya, to the base of the Tethyan sequence in the High Himalayas. So India was one contiguous plate. The first effects of the continental collision occur in two zones of high-pressure metamorphic rocks that we see. One is in North Pakistan in the Kagan Valley, and the other is in northeastern Ladakh around Somarari. And these are ultra-high pressure eclogites. Eclogites are high-pressure rocks composed of garnet and anthracite with indicative high-pressure minerals like coesite, which is the pseudomorph of quartz at high pressure. And even microdiamonds have been found as tiny little inclusions in these rocks. So these rocks indicate that the ultra-high pressure metamorphism in the leading edge of the Indian plate are in rocks that were subducted to over 100 kilometers depth during the initial continental collision and then returned to the surface. So this is the famous coesite eclogite boulder in Kagan, which is now pretty much impossible to get into. We managed to get in there for 3 or 4 years before all the political turmoil occurred across the border in Afghanistan. So these rocks are really interesting because their uranium-lead ages are very close to the timing of collision of India-Eurasia and closure of the suture zone, which was 50 million years. So 47 million years, the leading margin of India was subducted down to almost 30 kilobars, which is equivalent to about 150 kilometers depth, converted to eclogite in the coesite eclogite field, and then very rapidly exhumed back up the same subduction zone within 1 million years to the surface. It's not quite clear whether they're related to the final stages of ophiolite abduction, like we see, for example, in Oman, where there is also eclogites in the basement, or to the very first effects of the continental collision. It's likely that one process led directly onto the other. So how do we date the India-Eurasia collision? Well, there's several ways to do it, but the most bomb-proof one is the sedimentary record. This is a mountain in southern Tibet, Shiguri Shan, which shows the transition between the lower Eocene shallow water marine limestones. These are absolutely full of foraminifera, nummulites and acylinas and things like that. And it transits into a continental red bed molasse sequence up here. So the final marine sediment is this band here, which contains fossils of planktonic foram zone 8, which is equivalent to 50.5 million years. And this is extremely well constrained paleontologically. So we know that by 50 million years, there was no more ocean left between India and Asia. The two plates had collided, and the rocks started to deform, folding and thrusting and crustal thickening. So this picture here is taken from the middle of the Zanskar Himalayas, looking north towards Ladakh, and it's comprised entirely of unmetamorphosed shelf carbonates, mostly of upper Triassic, Jurassic, and lower Cretaceous age. The yellow lines are just tracing around bedding, so showing the fold structures. And the red lines are thrusts, where the fold has actually detached and moved. But this is the mechanism whereby the Himalayas were thickened in order to create the high pressure rocks that you see along the base of the mountain belt and in the greater Himalayas. So Indian plate collide with Asia, you start folding and thrusting, and over about 40 million years, you end up with the crust that's double the thickness of normal continental crust. And with the increase of pressure and temperature as you go down, the greater Himalayas are the metamorphic equivalent of these rocks up here. So the ophiolite is very rarely exposed along the Himalayas. The Spontang ophiolite in Ladakh is by far the best one. They're not exposed because they're the earliest thrust sheets that were transported from the Tethyan Ocean onto the leading margin of India prior to collision. And therefore, they were the first to erode. And it's only a few areas, like in this area in Ladakh, where the ophiolites are still preserved right up at the highest structural levels. And beneath that, you have these spectacular cliff sections. This is the main Zanskar Gorge, which I'll show you a few pictures of in winter when we did the traverse in winter one year. And these are the folds and thrusts that relate to the crustal thickening of the shelf carbonate sequence. So this is a picture taken from the bottom of that river. We did a ski trip in the middle of winter, January, back in 1995, 4 of us. We spent 2 weeks hiking through this absolutely freezing, frozen river gorge, mapping the geology, and then skied out from Padam out to Kashmir. So now in summer, it looks like this. It's a delightful place to go. This is just north of Padam, a very spectacular fold and thrust belt in the Tethyan sediments. And this is the mechanism by which these rocks were crustally shortened and crustally thickened. As you go up towards the suture zone, this is now taken just east of Leh, at the Indus Molasse. All of this sequence here is the post-collisional molasse that formed in a deepening basin, actually along the suture zone. And when you reconstruct all those folds and thrusts, you end up with a stratigraphy that looks like this. So the blue are the last final marine sediments, and you can see that the final one here is P8, planktonic foram zone 8, 50.5 million years. And after that, everything was continental. Red beds, lacustrine, conglomerates, fluviatile, and spectacular exposures of this everywhere throughout the Ladakh along the Indus Valley, and then unconformably overlying granites that have been very well dated as young as 47 million years old here. So we can infer the erosion or history of the collision process by looking at those sediments in the Indus Molasse Basin. Well, a few pictures here to show you what the country looks like. These two are taken out of the window of the airplane flying from Srinagar to Leh in Ladakh. This is Nunkun, highest peaks of Kashmir. Absolutely spectacular mountains. And you might think, well, it's impossible to actually get in there and do the geology, but there's actually 4 trekking routes that go across these mountains over into Kishtwar, Kashmir, and Himachal Pradesh. And over the course of a very long postdoc, I've done all of them. You start off in the north here, up in the Ladakh region, and this is a typical trekking route along one of the rivers that cross-cuts all of these structures to the south. And in the days when we were working in Ladakh, which was in the late 80s, early 90s, Leh was a fantastic place, almost completely unspoilt by modern civilization, which mostly involves sort of horrendous new architecture, military bases, and all sorts of dreadful things. But here is the old palace of Leh, ruled by the king of Ladakh, and it's very similar, sort of smaller version of the Patala Palace in Lhasa. And trekking there was an absolute pleasure. Once you left Leh, you were out in the villages and the gorges where nothing has changed. The only barrier being crossing these major rivers. Well, in the old days, they used to have spectacular rope bridges, which used to swing around as you crossed them in the middle. So we used to just pack, a month's worth of food onto a horse, hire a local guide. This is a good friend of mine, now died, unfortunately, Sonam Targis from Marka, and head off into the unknown. And we were doing traverses from north to south across the entire Ladakh, Zanskar, Himachal Pradesh region, camping out, cooking all our own food, and crossing these wonderful old swing bridges on ropes. Most of these bridges are gone now. They've either collapsed or been replaced by Indian Army aluminium bridges. And then everywhere in Ladakh, you go through these incredible, it's a wonderful Buddhist settlements in Ladakh, and they have these festivals. This one here is in Spituk Gompa in Leh in the middle of winter, so there's no tourists here at all. We were the only gringos around. It was absolutely spectacular. And having done about 5 or 6 field seasons in Ladakh, my first PhD student there, Ben Stevenson, I told him about this this epic trek that is very famous now. It's one of the very few winter treks you can do, walking entirely on the frozen river. And it's the only way out of the Zanskar Valley in winter. If you have a major problem or whatever, it's a 12-day walk along the river, and 10 days of it is walking on the ice of this river, which sometimes can be sheet ice here, nice smooth walking, and sometimes can be horrendous. This is a very fast flowing river. You definitely don't want to fall into it. They'd never get you out, and it's -10 at night, camping in caves along the route. But it was one of the most incredible treks I've done. And we hired these 4 local Zanskari people that used to know the route, and particularly where the caves were, that you could have a fire at night and that sort of thing. Okay, so going back to the geology, I've got 4 diagrams here which sort of run through each major phase of the post-collision process. So this is the Indian plate on the left, Archean Indian shield overlain by thick Proterozoic sediments, overlain by a classic Paleozoic Mesozoic shelf carbonate sequence with an abducted ophiolite, spontaneous ophiolite on top. The Indus Molasse Basin forming here along the site of the suture zone. Well, the first thing that happens is that TM is Somarari. These are the eclogite rocks that are now in the far northeast corner of the Indian plate. And these were part of the Indian passive continental margin sequence, mostly Ordovician lower Paleozoic rocks that were subducted down to at least 100 kilometers depth and then brought back to the surface again to become entwined in the main Himalayan crustal thickening phase here. These are the folds and thrusts that I showed you in the shelf carbonate sequence. We're looking here at a crust that's probably 45 kilometers thick, down in kyanite grade metamorphic pressure temperature conditions. So we're now looking at rocks that were in the surface, being buried down to 10 to 12 kilobars, 40, 45 kilometers depth, intensely folded and thrust and metamorphosed through regional Barrovian metamorphism up to kyanite grade. And the kyanite grade rocks, we've got uranium lead monazite ages between about 42 and 30 million years. So they were the earliest part of the Barrovian regional metamorphic sequence. And then we have a decompression as the rocks go increasing in temperature, but decreasing in pressure. And this is where kyanite reverts to sillimanite. Sillimanite is the high temperature polymorph, aluminium silicate polymorph, and it's associated with a lot of migmatite. So sillimanite muscovite, sillimanite cave feldspar melting produces eventually the Luca granites that are famous in the Himalayas. And those are all much younger. Those range from about 30 million years up to about 16, the youngest, with a peak of a sillimanite grade metamorphism and Luca granites around 22 to 20 million years ago. So here is a picture taken from a friend of mine, Leo Dickinson, who crazily flew a hot air balloon across Everest many years ago. And the hot air balloon took off here from Gokyo in Nepal and rose very gently up to the jet stream. When it hit the jet stream at about 8,000 meters, they rocketed across the summit of Everest with about 100 meters to spare or less, and eventually crash landed in Tibet. But he did, hanging out of his basket, he took these incredible pictures of the east face of Everest. This is Lhotse, Everest, South Col, going round to Nuptse, the horseshoe. So the climbing route from Nepal goes behind this. And then this is the Rongbuk Valley here going down into Tibet, with all the peaks of Chowoyu and all the peaks of the Khumbu Himalayas, the Rolwelling Himalayas over here. Magnificent picture. And this is another picture taken actually from a commercial flight going from Kathmandu to Bhutan, Paro, looking at the Lhotse Ridge. This is the Nuptse-Lhotse Ridge, Everest in the background. The Western Coombe and the climbing route is the other side of the Nuptse Ridge. And this is the spectacular granites that form the guts of the Nuptse mountain range here. So I spent 7 years mapping the Everest Massif, both from the Nepal side and the Tibet side, along the Rongbuk Valley and the Kangshung Valley here, which drains into the Arun. And this is the map that I published in 2003. The later edition has the addition of Makalu in here, where we had a 3-year project looking at all the Makalu and the Barron gneisses. Everest is an incredible place to work, really. It's the climbing scene on Everest is absolutely crazy. But in those days, this was in the 90s and 2000s that I did all this work. The climbing was important, and hundreds of people going up there every year, but now it's literally in the thousands, and you have to queue, pay huge amounts of money. So climbing Everest is a nightmare. But everyone just goes up the same route. They go up here to base camp and then climb up here through the Western Cwm up to the Everest here. You go round any of these side valleys going off here, you never see anybody. It's completely pristine, beautiful country, and the geology is absolutely spectacular. So here's a cross section from Everest looking north along, this is all in Tibet, along the Rongbuk Valley. And we're looking along the South Tibetan Detachment, which is one of these low angle normal faults that puts sedimentary, unmetamorphosed sedimentary rocks over metamorphic rocks. The Everest series is sort of intermediate green schist upper amphibolite facies sequence, and then the orange and is all sillimanite gneisses, high temperature metamorphism, and leucogranites, which form these incredible lateral sill sequences that go on for forever and ever. This is the big Nuptse granite that's a ballooning sill dated at 23 million years. These are a couple of kids in the Solukhumbu pointing out where the top of Everest is. And the summit of Everest is actually made of Ordovician unmetamorphosed limestones. I have about 20 samples collected from various friends guides who've been up there. And Conrad Anker, David Hamilton, John Tinker in particular, and Kenton Cool in particular, sorry. And the rocks up here still have relict traces of fossils in, particularly crinoid ossicles and fragments of trilobite, and they are Ordovician, whereas the yellow band, which is a metamorphic sequence, used to be Cambrian limestones belonging to the base of the Tethyan sequence here. So we have been comparing the Cambrian in blue and the Ordovician sediments with this is the Everest sequence here that we're looking at in this picture here. Comparing it with well-known stratigraphy both in Tibet and in India, particularly in the Spiti Valley and in Zanskar. So when you look at the metamorphic sequence, I had a couple of PhD students, Micah Jessup from the US and John Cottle, who was a New Zealander doing his PhD in Oxford. And between the two of them, they were looking at the pressure temperature conditions of the GHS metamorphic sequence all the way up from the main central thrust zone down here. And you'll notice that there is an incredibly intense inverted metamorphic sequence. So the higher up you go, the hotter the rocks. So you're going up from garnet, staurolite, kyanite, sillimanite, muscovite, sillimanite, K feldspar. And then when you hit the sillimanite K feldspar isograd, you're immediately into migmatites. These are rocks that are partially molten. And then as you walk up from the airport, if you fly into Lukla, you arrive here and you're already in sillimanite grade gneisses and migmatites. And that sequence lasts all the way up until you get up to Everest Base Camp. So all of this is in high temperature and relatively low pressures. Pressures are only about 4 to 6 kilobars, but the temperatures are extremely high, getting up to about 800 degrees centigrade. And this is where all the migmatites and the partial melting occurs. More on this later. But when you get up to the Everest itself, the Everest Base Camp, this is the Nuptse face. The low angle normal fault clips the summit of Everest and goes north all the way down the Rongbuk Valley down here. So it's no easy matter trying to map out metamorphic isograds, especially in this terrain, because you're looking at three-dimensional structure that's actually a chemical change of composition rather than a physical structure like a fold or a thrust that you can measure and see in the field. But we've done now an enormous amount of work finding out the pressure temperature conditions along this transect from the main central thrust south of Lukla all the way up to Everest on the Nepal side and all the way down the Rongbuk Valley on the Tibet side. And on the Tibet side, the South Tibetan Detachment, which is this low-angle normal fault, it's an absolutely spectacular structure. Puts high-grade unmetamorphosed sedimentary rocks up here over partially molten sillimanite gneisses, leucogranites and migmatites down here, with an intense right way up metamorphic sequence through the top along the Rongbuk Valley. And this is what it looks like. Everest is 2 days walk to the right. This is the Rongbuk Valley, which is the main road you drive up to Rongbuk from Lhasa. And this is the detachment here. So a lot of people don't believe in low angle normal faults because they disobey all the Andersonian tectonic laws that you can't have a low angle normal fault less than 35 degrees dip. This one here is undoubtedly there. It puts unmetamorphosed sedimentary rocks over high-grade metamorphic rocks and marbles. You can map it out for 70 kilometers from the summit of Everest to here, where it disappears north under the Rongbuk Valley. And we've got very good samples from all of these rocks. These are Ordovician sedimentary rocks with remnants of fossils in, and these are leucogranites and sillimanite gneisses in the footwall. These are structure contours on the South Tibetan Detachment, which is one of the most spectacular low-angle normal faults in the world. They occur all over the place now. They're in metamorphic core complexes in the western US. They're in famous core complexes like Naxos in the Aegean, and they are undoubtedly there. And the reason people don't have trouble figuring out why they are operating at low angles during active motion is that all the motion is occurring on the footwall. So the hanging wall stays stationary, and it's the footwall that's moving out. And in Everest, you can reconstruct this. So here is a reconstruction of Everest. The summit is right here. The Rongbuk Valley is here, going off into the Tibetan Plateau. We know that metamorphic samples taken from Everest Base Camp on the Nepal side of Everest are 3, 4, 4.5 kilobars, which if you reconstruct them, this is a very conservative reconstruction, depths of maybe 15 to 20 kilometers. And assuming that the South Tibetan Detachment maintains the same angle of dip, low angle, which is perfectly reasonable, then these rocks must have come from 100 kilometers north of Everest, extruded out in order to juxtapose against both of these rocks today. This is the same normal fault taken from near the top of Shishapangma, which is an 8,000 meter peak in Tibet. This one here is looking north. We're now about 100 kilometers west of Everest in the southern Tibet region. This is the only 8,000 meter peak fully in Tibet. And again, the same structure is right here. These are Cambrian, Ordovician, unmetamorphosed sedimentary rocks. And these are leucogranites that we've got ages of 20 and 17 million years. So this is a very young, very active low angle normal fault with at least 100 kilometers of motion of the footwall as it's extruded out to the south. The Tibetan Plateau over here is at an average elevation of just around 5,000 meters. And our base camp here was 5,250 meters. And the summit of Shishapangma was 8,000. So this is a big, big structure, South Tibet Detachment. When you get into the footwall rocks, they're very complicated. And these are various outcrop samples taken from just north of Everest in the Kangshung region, where you can see the sort of things we're doing. We're mapping out the structures here. So these are folded high-grade metamorphic rocks and leucogranites, folded, cut by a younger set of leucogranite dikes here. And then when you get samples from here and date them, you can get a pretty good idea of the timing of deformation, metamorphism, melting, and timing of the South Tibetan Detachment. So it may be a surprise to some people that the highest mountain on Earth, Everest, is cut by 2 low-angle normal faults. Normal faults are normally associated with regions of extension, like East African Rift, Basin and Range, or the North Sea, somewhere like that. But here we've got the highest peak in the world that's clearly in a compressional mountain belt, has been for 50 million years, still is active today. And there's low-angle normal faults, putting lower pressure temperature rocks onto higher. It's one of the major new discoveries of structural geology, I would say, of the late 2000s, the importance of low-angle normal faults and extrusion of the metamorphic footwall to form these core complex type structures. So here's another picture of the Nuptse granite. This is from one day south of Everest Base Camp, looking along the Imja Kola here. You also have mapped out some very interesting ductile shear zones and thrusts, fully within sillimanite grade temperatures. This is the Nuptse granite here. This is an east-west section, so we're looking parallel to the strike here of both Everest and Lhotse to the south. So this is the peak of Gai Chung Kang, which is just below 8,000 meters, which means it's not bedraggled by all these crazy mountaineers wanting to climb the highest mountain. It's only had a few ascent, and it's spectacular. It's got these two low-angle normal faults, Chomolungma detachment, Lhotse detachment, unmetamorphosed sediments, intermediate green schist amphibolite grade metamorphic rocks, and leucogranite. Just on the, this is the peak of Amadablan, which is just south of Everest in the Khumbu region of Nepal. Absolutely spectacular mountain. When you go in there and you map out all these cliff sections, these are the leucogranites. Everest is just off to the left. The South Tibetan detachment, which clips the top of Everest, the Chomolungma detachment, is roughly up here. And you can see that all these leucogranites are intruded as sill complexes. And then the dikes that feed the next sill up are all bent around to the north during active motion on the South Tibet detachment. Again, this is an unnamed peak west of Pumori, just a day's walk from Everest Base Camp in Nepal. You can see these magnificent structures of these leucogranite sills with little dikes here feeding the sill complexes higher up. It's like a chessboard of leucogranite melts forming. Absolutely incredible. They're all to stop at the Lhotse detachment. And then the Everest series is this intermediate series. This is looking straight up the north face of Everest, now to the Chomolungma detachment here. And this is the big fault that puts unmetamorphosed Ordovician sediments over metamorphosed Cambrian calcsilicates of the yellow band. So this rock here, this was collected by the great Ed Hillary himself on Summit Day, 29th of May, 1953. And this is, we now have about 20 odd samples of these rocks from the summit of Everest, which I'll show you have got these remnant fossils in. This is clearly a sedimentary rock. It's a muddy limestone that formed in the Ordovician. This one here was taken on the first summit attempt by Evans and Bourdillon 3 days earlier. They didn't get up to the summit because their oxygen sets failed, but Evans collected this sample here from the yellow band, which is clearly a metamorphic rock. So the detachment lies between these two rocks here. These are the crinoid ossicles taken from the summit rocks of Mount Everest. This is the remnants, so I'm told, by Owen Green, who's our resident paleontologist. This is the ossicle here, seen under cross-polarized light. This is the stem of the ossicle with a single calcite crystal around it. And these are fragments of crinoid ossicles, and there's also little bits of remnant trilobite fragments in there. This is what they look like today. You very rarely see them preserved like this. What we're looking at is a little cross-section through one of these ossicle stems here. And these are all collected from, sorry, not those ones, but we have quite a few of these ossicle collections from the Ordovician series of Tibet. Okay, so to summarize what's going on in the metamorphic sequences of the Himalayas, this picture here is taken from Poon Hill, looking west across the Kaligandaki, which is supposedly the deepest gorge in the world between Dhaulagiri and Annapurna. It's an absolutely spectacular sequence. So the Kaligandaki gorge is deep down in here. And what we can see here is the main central thrust way down in the south of the high mountains with the inverted metamorphic sequence, biotite, garnet, kyanite, sillimanite. And then this low angle normal fault, which chops through the base of Dhaulagiri. Dhaulagiri and Annapurna are the only two of the 8,000 meter peaks that are fully within the sedimentary sequence of north of the South Tibet detachment. All the others are either in leucogranites forming at the top or like Everest, just clipping the top of the South Tibet detachment here. So we have a sequence of pre-collision ophiolite abduction, spontaneous ophiolite in Ladakh, crustal thickening during that and following the collision of India and Asia, largely by folding and thrusting, crustal thickening, and then post-collisional shortening of at least 500 kilometers and thickening to approximately double crustal thickness today. We have syncollisional eclogites dated at 50 to 47 million years, which could be the tail end of the ophiolite abduction as the continental crust is dragged down the subduction zone, which leads on to the full Barrovian regional metamorphic sequence. Kyanite melts here around 30 million years ago, and we have these little pods of kyanite melting, which indicates deeper pressure crustal melting. And then decompressions form the major sillimanite, muscovite to sillimanite cave feldspar crustal melts, which is where most of the Himalayan leucogranites are forming today. So here's a picture of Dhaulagiri. This was taken during a filming trip we did with the BBC many years ago. Looking right across at Dhaulagiri, there's three rocks here. There's a kyanite gneiss, 12 kilobars, 35 million years. And this is a clinoproxene tremolite cave feldspar, high-grade metamorphic marble, formed at 9 kilobars, and these are sedimentary rocks, Cambrian Ordovician sedimentary rocks, which have never been buried. So somehow we have to juxtapose those three samples together, which is where we see them today. And again, using the same restoration tricks, we can extend the kyanite gneisses down here to 40 kilometers depth, and they have come from at least 100 kilometers to the north of where they are now beneath Dhaulagiri. This is very similar to the detachment in Everest, where we've got a minimum extrusion of 100 kilometers of the footwall rocks relating to extrusion of the greater Himalayas relative to the Tethyan Himalayas above. So what do the guts of the Himalayas look like? This is on a trek that I did many years ago now from Kashmir over towards the Chenab Valley in western Himachal Pradesh, and then leading eventually over into Zanskar, Gumbarangjam Massif here. And you can see all the isograds, kyanite, staurolite, garnet isograds. This is right way up metamorphism, telescoping into this huge ductile shear zone along the South Tibet detachment here, which is called the Zanskar shear zone in the west. And then in the guts, in the core of the metamorphic complex along the Chenab Valley, this is, here's the main trail. There's a pony, there's a horse and a man there to scale, looking down to the Chenab River, and these are horizontally intruded leucogranites within sillimanite gneiss. Over in there's the metamorphism of the Himalayas leads on to eventually to crustal melting. As soon as you cross the sillimanite cave feldspar isograd, you have water saturated melting or dehydration melting. And these are the rocks that are melting. These are pilitic rocks, which started off life probably as Proterozoic mudstones and shales, metamorphosed to kyanite. These are kyanite crystals here, these blue bladed crystals, and the red are garnet. And eventually to sillimanite gneisses and partial melting. So these are classic migmatite textures that we see from the Zanskar range here. So the Himalayan granites are 100% crustal melts, S-type granites. There's no mantle component at all. They have a local migmatitic source formed at very low pressures, but reasonably high temperatures. And they're forming largely because of a very high internal radiogenic heat production from this Neoproterozoic black shale that forms the protolith. And they're intruded as multiple sill complexes between these times here, with a peak around 21 million years. So we climbed a new route on Shiverling way back in the good old days, and when I was young and fit, and managed to get samples from the summit all the way down here. This is not only for dating of the crustal melting time, but also using lower temperature thermochronometers like the argon-argon fission track to indicate the uplift exhumation history of those rocks. So At the highest temperatures, there's another phase of granites that actually has a large amount of magmatic cordierite in it. These cordierite crystals, these big green things here, which have been retrograded now to pinite. But most of the mountain of Makalu forms these beautiful cordierite leucogranites, which are evolving from melting of the barren gneisses. And these have a slightly younger age than the main Himalayan granites that we see on Everest, for example, 15, 16 million years. So this is taken from just above Makalu Base Camp in Nepal, looking up, the summit of Makalu's up here. And these are the cordierite granites, the late cordierite granites that intrude all the earlier rocks here. The earlier Himalayan tourmaline 2 mica granites are these things here, which are truncated by these later 15, 16 million year old cordierite granites. Makalu is a spectacularly beautiful mountain. This picture here is taken actually from the Tibet side, looking across the Kangshung Glacier down here to Chomolungma, 2 kilometers of vertical granite, leucogranite there, and the summit of Makalu, 8,700 meters over here. Just to show you the complexities of some of these granites, this is just one boulder taken near Makalu Base Camp with 6 different cross-cutting phases of granite. And these really are different cross-cutting phases, because this granite here was intruded, cooled, when this granite was injected into it. So, and all of these granites probably formed within 1 or 2 million years of each other. We have quite a few dates from Makalu, but not enough to date every single one of those phases. So these are the 2 dehydration melting reactions. One that produces the main tourmaline granites is this one, the Muscovite dehydration reaction, goes to K feldspar, sillimanite, and melt. And the other higher temperature one is the biotite dehydration reaction, where the cordierite is the stable phase at low pressures and garnet is stable above 5 kilobars. So we're getting these rocks from an early megmatitic source. You have a series of hydraulic fracturing that's opening cracks for the melt to intrude passively. There's an enormous amount of over-pressurized volatiles there, which causes these huge tourmaline, beautiful tourmaline crystals to crystallize in the pegmatites. Some of the larger intrusions are up to 4 or 5 kilometers thick. These are almost laccolithic type sill complexes. And throughout all of this, the South Tibet detachment formed a passive roof. So all the motion was extrusion along the footwall. When you get into the guts of the Everest Massif, this is now on the Kangshung side of the eastern side of Everest. This is an absolutely amazing outcrop, which is almost like we're in the middle of the channel here, where all the earlier biotite sillimanite grade gneisses and the early tourmaline leucogranites are in these boulders surrounded by this very young Everest leucogranite here, which forms most of the lower part of Mount Everest. We can date the metamorphic phases using monazites that's growing in equilibrium with the high-grade metamorphic rocks, and we can date the leucogranites using zircons and monazites as well. So here's a summary of all the geochronology. This is a bit of an old diagram, so I'm going to skip through it pretty quickly, but the Everest Pumori leucogranites are here. The youngest ones, which are truncated by the Lhotse detachment here, and the Everest series green schists here, and the Chomolungma detachment cuts down and truncates everything underneath it. And one of the things John Coffell mostly did was doing all the uranium lead dating. He found that there was a northward younging of ages of both metamorphism and melting as you go from Everest northwards into Tibet. So these rocks here in the Amadrima Massif, which are the northern extension of the high-grade metamorphic rocks as you go northwards into Tibet. When you plot all these ages on a temperature versus time diagram, India-Asia collision here at 50 million years, crustal thickening here progressively during prograde metamorphism. The first kyanite grade melts are starting around here, 35 million years, and then a decompression to sillimanite metamorphism here. And as soon as you start melting, regionally melting those rocks to produce leucogranites, those rocks are have very low friction, so they are ductilely moving very fast. And the geochronology shows that within 1 million years of melting, these rocks have cooled down to anything like 300 degrees through the argon-argon closure temperatures here. So it's the crustal melting that initiates lateral flow, rapid cooling, and the beginnings of exhumation. And this is a process here that we term channel flow, where you have an inverted metamorphic sequence along the base, the main central thrust, sillimanite going down to kyanite, staurolite, garnet, sedimentary rocks in the lesser Himalayas here. And you have a right way up metamorphic sequence along the top, both in Zanskar and in Everest, all the way along the whole of the South Tibetan detachment. You have this right way up metamorphic isograds truncated by this ductile shear zone and brittle fault, which means that all these rocks of the high Himalayas were extruded to the south, with the ages getting progressively younger as you go towards Tibet down here. And you can actually match those with the in-depth geophysics seismic section where they shot deep crustal geophysics right the way across Tibet. So how do we know what the composition of the lower crust here is? Because you never see any Archean rocks in the Himalayas. You never see any high pressure granulites, but what you do see are these spectacular shoshonitic dikes that cut. Shoshonites are mantle-derived lampropheric type rocks that intrude up, and during the passage up through the crust, it's plucked off tiny little xenoliths here, which are of an incredible composition. They're mostly mafic and felsic granulites formed at extremely high temperatures and very, very high pressures, 25, 26 kilobars. These rocks have tiny xenoliths in them that you can date, zircons and monazites, and these are the same age as the youngest leucogranites that are extruding in the Kangshung face of Everest, so 14, 16. So we absolutely know that by this time, the Himalayas had a crust that was at least 70, 80 kilometers thick and was producing granulite facies metamorphism at that time. And as I said, you could extend these from the Himalayas. So this is a picture taken across the whole of Tibet, taken from the in-depth model. This is from Georgi Hetenyi's publications, and you can trace the moho here from beneath India, going all the way down to something like 80 kilometers. There's a very strange double moho under the latter block, which some of us interpret as bounding eclogitic lower crust. So if you take a granulite facies rock here, transport it down to depth, you convert the granulite to eclogite. Eclogite has the same density as the mantle, and that is actually what is holding up the Tibetan plateau today. Okay, so that's the story of the Himalayan metamorphism deformation, and that is remarkably consistent for 2,000 kilometers along the whole length of the Himalayas, at least from the Ladakh Zanskar to Arunachal Pradesh, Bhutan region in the east. With two exceptions, and those are the corners. The northwest corner is the Nanga Parbat syntaxis in Pakistan, and the one on the east is the Namche Bawa syntaxis in southeast Tibet. Both of these areas have been through the entire metamorphic history of the Himalayas, but they also have an incredible, very young component of melting. These are Pliocene, Pleistocene, high-grade metamorphic rocks, sillimanite, cordierite, migmatites formed at depth beneath an 8,000 meter peak up here. So I went up to Nanga Parbat several times. I was on my own collecting samples, and the highest I got to were these outcrops here, which were up at about 6,500 meters. But they come from the core region of Nanga Parbat here. And the most amazing thing about these rocks is that they have uranium-lead monazite ages. These are recording ages of when that rock was at 700, 750 degrees temperature, as young as 0.71 million years ago. That is incredible. Those are quaternary Pleistocene high-grade migmatites and metamorphic rocks that now form the highest part of Nanga Parbat up here. So you've had at least 17, 18 kilometers of erosion in the last 700,000 years. This is what the rocks look like. Beautiful migmatites here with these extensional veins. The big green minerals here are cordierite and sillimanite. So you have these garnet cordierite veins with tourmaline leucogranites, spectacular cordierites in here. And some of the youngest tourmaline granites dated 0.7 million years, which is quite amazing. The eastern syntaxis is around here in Tibet, Gyalapuri, Namche Bawa, where we've tried to get into several times, but unfortunately it's impossible to go down the gorge. The Chinese are building hydroelectric dams down there. They don't want anyone from outside to see what's going on. So what happens in Tibet to the north? Well, Tibet is largely like this. It's very flat and somewhat boring. You can drive across Tibet for 5 days and see nothing except scenery like this. There's very little erosion exhumation because it's so dry, but it's all of this region here in yellow is above 4.5 to 5 kilometers above mean sea level. So it's extremely high elevation, very low relief, very low erosion because it's in an arid climate. Okay, so here's 2 cross sections across the Himalayas and the Karakoram in the west. This is mostly in North Pakistan, the Baltoro region. And this is the central Himalayas and the Tibetan Plateau north of Nepal here to the east. And the base of the crust is constrained from the in-depth seismic results, where the deepest crust is actually under the Karakoram at 90 kilometers depth. These are the Miocene granites of the Baltoro. Above that, which is a whole different story. But all the geophysical experiments across Tibet are all pretty much in agreement that Indian lower continental crust and lithosphere goes to at least halfway across the plateau before it nosedives down. Although the plateau is almost universally high and thick, the tectonics are completely different from the south and the north. And you can trace that through some of the lampropheric crustal melts that are occurring across Tibet today. So the Karakoram is an absolutely incredible, spectacular mountain range. I don't have time to go into this now, but just to say it has a pre-collision Andean type geology. It has a full range of post-collisional metamorphism, crustal melting, producing the Baltoro leucogranites here. None of this is exposed in Tibet, possibly because of the lack of erosion and exhumation. In the Karakoram, we've got phenomenal erosion exhumation. And eastern Tibet, north of the Namche Bawa syntaxis, again, all of these mountain ranges are pretty much unknown geologically. There's still a huge amount of work to be done out there. As you come around the eastern syntaxis, the structures end up down here in Tibet, in Burma. We've been working in Burma for the last 7 years before the military coup. Fantastically interesting country, trying to trace these Himalayan structures around the corner down into central Burma. Okay, so that's really a talk on the Himalayas, and I think I'll just end it. I've got a few pictures of the earthquake to finish with, but this is a picture of Taksang Monastery in Bhutan, the famous Tiger's Nest Monastery, which is a beautiful place. And they have this very becoming quotation here from the Buddhist scripts: the becoming, the being, and the vanishing of all worlds, and the impermanence of all existing things, which is very appropriate for the Himalayas, because you build up these mountains, erosion tears them down, take the debris all the way down to the Bay of Bengal in the Indian Ocean. So nothing really is permanent there at all. And this is really brought out from the Gorkha earthquake of 2015, which went off in this region here, just halfway between Kathmandu and Pokhara, north of the town of Gorkha. And this was a catastrophic earthquake. It was nothing like as big as it was supposed to have been to take up the strain that we know is down there. A magnitude 7.8 was enough to do an enormous amount of damage. And this is all the uplifted area along the region that's split. But the interesting thing about this earthquake is that from the epicenter in Gorkha, it broke about 170 kilometers of the plate boundary along the main boundary thrust, which is the deepest, most active fault of the Himalayas. What should have happened is that earthquake rupture, which had like 7 kilometers of horizontal motion here, And these mountains here were uplifted by over a meter, 1.1 meters instantly in a few seconds. That strain should have been taken up by one of these frontal folds and thrusts at the base down here in Chitwan, and it wasn't. None of these moved at all, which is a big problem because it means all the strain is still down there. So here's a cross-section of the Ganesh Himalayas down through the Kathmandu clip. And this is the rupture here. The earthquake went off at very shallow depth, only about 17 kilometers depth, which is why there was a lot of damage. These mountains here rose by about a meter. In fact, all of this area tilted down to the north. Mount Everest actually went down because it was tilting. It will rebound again, but it went down by a few centimeters. And unfortunately, the rupture split from here to here and 150 kilometers along the strike, but it did not extend up to one of these active faults at the southern boundary, which it should have done, which means there's another fault, there's another big earthquake just waiting to go off. And we don't know whether it's going to happen tomorrow or in 100 years' time or 1,000 years' time, but it will definitely happen at one stage. As long as India continues to push north, it will definitively happen. So the greatest areas of earthquake rupture in the future are the areas south of Kathmandu, down here to the Chitwan Hills, and the region from Pokhara to the Gorkha epicenter, which did not break at all during the 2015 earthquake. There's some spectacular things you can do now with geodesy. This is a picture from John Elliott paper. Each one of these contours shows the uplift associated with the hanging wall uplift of the mountains to the north of Kathmandu. And then it produced an incredible amount of damage. There were old Nuwari temples in Durbar Square in Kathmandu that collapsed. Tragically, a lot of them have now been rebuilt through the UN, which is extremely good. Rebuilt in the old style again, which is also really important. This is a picture of Langtang Lirong. This is the first major peak we attempted to climb through the south face here in 1980. We didn't get to the top, but unfortunately the 2015 earthquake loosened the whole of that south face, which completely collapsed and now buried entire villages. So this is all the debris which came straight down the climbing route that we tried on the south face of Langtang Lirong. And it's absolutely tragic. There was a whole village here of several hundred houses completely buried, no survivors at all. That's what it looked like before in 1980, and all of that is now under that pile of debris. So these mountains are incredibly active. This is taken from our Camp 2 or 1 looking down the region that broke, and all of these rocks here just collapsed straight down. The Langtang village is down in the valley down here. Incredible high incision of the river systems up there. This is looking the other way, up the Langtang Valley to the Jugal Himal. All of these mountains here were formed in the same way by progressive earthquakes, uplift of the hanging wall. On Everest, there was a massive avalanche. All of this debris here from the border ridge region collapsed, and the air blast went right the way through Everest Base Camp, which is down here. Several people, I think 15 people were killed just in their tents at Everest Base Camp. Above the epicenter of the earthquake, this is the destruction that happened. This is Laprak village in the Burhi Gandaki. Almost complete destruction. Every house was destroyed. Well, all our porters and villagers came from this village on the opposite side of Burhi Gandaki. This is an old picture pre-earthquake. Beautiful little village right up on the top of the tree line. You can see Manaslu and the whole of the Ganesh Himal from just above here. And something like 20 or 30 houses collapsed. The school here completely collapsed. It was very lucky that happened on a Saturday afternoon. So anyway, to cut a long story short, we set up a charity which rebuilt a lot of the houses here. We built a completely new school from where this picture is taken. And there's now a little village clinic, hospital up here as well. So we have done a lot to alleviate, at least from this one village. So as John mentioned, I wrote this book, which I can highly recommend if you want Christmas presents or whatever. It's about the whole history of the Himalayas. And the history of a 28-year postdoctoral fellowship, for which I'm grateful to NERC and a lot of other people towards. And with that, I will end it. Thank you very much for listening, and namaste.